from the University of Hyderabad, and he will actually present some Archean geology, and more specifically some work done on the Dharwar craton in southern India. Thanks a lot.
Thank you very much. I'm very happy to be here because in fact I'm not new to this lab. I visited this lab several times, I think from 1995 to 2003, several times I visited. We were collaborating with Hervé and Jean-François. Jean-François did his PhD in India. We did a lot of work together in India, Jean-François and me, and we have also published several papers. And I'm very much thankful to the lab and Martin for inviting me here. In this talk, I'm trying to summarize very briefly about the geologic framework and the crust forming events and the rates of continental growth in the Dharwar craton, more specifically. And since this, as I know that many of the audience are not specialists in Archean geology, for the first 2 to 3 slides, I just give a very brief introduction to the Archean. Then I go to the Dharwar craton. The outline of my presentation is I talk about very briefly about unique features of the Archean Earth, the geological and tectonic framework of the Archean Dharwar craton, and the microblocks within the Dharwar craton. This is the new aspect of science that we identified microblocks within the Dharwar craton with the cratonic framework. Then I just briefly talk about the time framework of the crust formation in individual microblocks, and finally how and when these microblocks were amalgamated into the cratonic framework. Well, now the fundamental question is why study of Archean Earth is so important. Because in the last 2 decades, study of the early Earth has taken backseat because more shift to the surface. And this is a global trend that even in our own country, the funding to work on the surface environment, surface dynamics is more easy to get, and for them they work the proposals on the deep crust. The regions research on Archean crust it took again some more new initiatives. That research on the Archean crust has been one of the major topics of global focus in earth and planetary sciences more recently, last few years, because globally there's a big demand for resources, and Archean crust contain most of the known strategic mineral resources. Then the other important reason is that knowledge accrued from the Archean crust is also fundamental to our understanding of the geologic history of and the tectonic history and the thermal history of the early Earth, and also it is also very important for our understanding of the shift from anoxic to oxygenated environments and the origin of life. So these are some of the important aspects where we get the more insights from the Archean cratons. Now, coming to the unique features of the Archean crust, this is compared to the modern Earth, Phanerozoic Earth. Archean is a major period of crust growth. Most of the crust growth models that have been presented, they indicate about 60 to 70% of the present day continental crust, preserved continental crust formed in the Archean. And Archean is also characterized by the high heat production and higher geothermal gradients. This is the high thermal flow or the geothermal gradients, or the hotter mantle is mainly because of the decay of long-lived radiogenic isotopes, uranium-235, potassium-40 and thorium-232, together with short-lived radionuclides like A26, I-129. So, and in addition to this, the huge accretion during the Archean, that has contributed to the high the thermal budget of the Archean Earth. And the most important aspects of the Archean cratons in all the Archean cratons, invariably they contain voluminous tonalite, tongimite, granodiorite. These are known as TTG suites. And the most prominent, the oldest, castern ice in Archean Slave Province, and also in southwest Greenland, in southern Africa, in Kapal, and in India, and of course in Australia also the very old crust, TTG crust has been documented. And the other, these are the typical TTG suites where we have the tonalite, granodiorite, and tongimite. And the other important feature of Archean earth is that the greenstone belts with comatiites. We have spinifex textured comatiites which are very well preserved in, first they were reported in Barberton in South Africa. Subsequently, they have been reported from other Archean cratons in Pilbara, Superior Province, in India, in Finland, in Brazil. So this is one of the most important features of Archean earth. Then the band iron formations. These are some of the most prominent lithologies in the Archean greenstone belts. Most of the time they confined to the summits, and these either TTG or the comatiites or the band iron formations. Such thick band iron formations are totally unknown in the modern orogenic belts. Then another important feature of Archean earth is the general absence of high pressure lithologies like agglomerates. So Archean earth is moderate pressures to low pressures, but relatively high temperatures. So the granodites are well preserved in most of the Archean cratons. Well, very briefly about the Archean TTGs. These are the grainizers, which are the most voluminous lithologies in all the Archean cratons. They were collectively called tonalite, tongimite, granodiorite suites by John and his colleagues, 1981. And coming to the sources of TTG, there is a general consensus among the scientific community about the sources. Most of the scientific community agree that these rocks derived by melting of mafic rocks, but there is some debate, particularly regarding the depth of the melting and the mineralogy of the residue after the melt. So, if amphibolite residue is considered, if the melting within the 15 kilobars, corresponding to about 50 to 55 kilometers, and the eclogite residue, it is more than 20 kilobars, more than 70 kilometers depth if melting occurs. And coming to the tectonic setting of TTG magmagenesis, this aspect is also, there is a considerable debate and discussion about the tectonic settings of the TTG magmagenesis. And there are three major models have been proposed for the origin of TTG magmas. Number one is, earlier this was mostly considered that the TTGs are generated by melting of the oceanic slab in the subduction zone at different depths. But subsequently, other workers proposed that the melting of the base of the oceanic plateau crust can also give rise TTG magmas. And more recently, people argue that the melting of oceanic crust in the subduction zone cannot produce, because the oceanic crust that is produced at the oceanic spreading centers is highly depleted. Such depleted crust, if you melt, you don't get the real TTGs. So people argue that there is two-stage melting. First stage, melting of the subducted oceanic crust gives rise to the arc magmas, so building up of arcs. Then the second stage melting, melting of the thickened arc crust at different depths can give rise to the TTGs. That explain most of the elemental characteristics of the TTGs on the global scale. Then the other most important lithologies in the Archean is the greenstone belts with comatiites. So this is quite unique because in the modern convergent margin or the continental margin or in the oceanic islanders, we don't find the comatiites. This is a unique feature of the Archean earth. And the greenstone belts, for many years, a lot of focus has been given to the greenstone belts because they were known for the mineralization, such a mineral, that is the reason. a lot of focus has been given. And these are the volcanosedimentary sequences, and they are known to occur in all the Archean cratons, and they are generally, their ages are in the range of 3,800 to 2,700 million years. And these greenstone sequences, mostly in terms of the volcanics, the basal sequences, volcanic sequences are mostly comatiites or comatiitic basalts or basalts. And when we go to the higher, we have the felsic volcanics, and these volcanic sequences are interlaid with sediments. And finally, on the summits, most of the greenstone sequences, they contain very thick banded iron formations. Then, coming to the comatiites, these are the ultramafic, high MgO, highly, very low viscous lava flows, which are mostly restricted to Archean cratons. One of the most outstanding features of these comatiites, they show spinifex structures. So these spinifex structures have been first documented in the Barberton, and subsequently similar rocks have been documented in other. But these rocks are known in the among the geologic fraternity only from 1969. Before that, these rocks were not known, comatiite, because they first documented along the Komati River in South Africa. So then similar rocks have been identified in most of the Archean cratons. Then, for example, in Pilbara, they have very good comatiite, Superior Province. In India also, we worked and we continue to work on these comatiites. Now coming to the Dharwar craton. Now, why Dharwar is so important? Because this is one craton where a large pristine crustal panel has been exposed. Because we can see in this one is a tilted panel of the whole Archean crust, where we can see the continuous transition from upper crust to the lower crust. So we have the pressure estimates along a crustal corridor right from 2 kilobars up to 10 kilobars. So a continuous crustal section has been observed, and this is one of the key regions of global focus, because it forms a wide time window from 3,800 million years to 2,500 million years. So this is one of the regions. So this is the geologic sketch map of, I would say, geologic sketch map of the Dharwar craton. Well, the boundary still little bit extends up to there is a river, large river system called Godavari River, and the southern boundary, this is the transcurrent shear zone that separate two crustal domain. In south, this is mostly Proterozoic domain. This is on a southern granulite, and the north of this transcurrent crustal scale shear zone, this is the Archean domain. So we have a clear, here there are no greenstones, no TTGs, it's only dominantly the sediments in this region, and some mafic intrusions. So and most of the rocks are Proterozoic in age. Well, coming to the geologic framework of the craton, like all other cratons in the world, the Dharwar craton also consists principally three rock types. The most voluminous TTG type, peninsular gneisses. Regionally they are known as peninsular gneiss. Because in the beginning of the last century, when the geologists worked, they were most common in every part of the southern peninsular India, so they named them as peninsular gneisses. Then we have the two generations of the volcanosedimentary greenstone sequences. Then the third important component is the chalcochrome into potassic plutons. So these are the major lithologies of the Dharwar craton. Well, here we can see all this, the open, the areas, without any color, they corresponds to the gneisses, and we have the two slightly different green color, green and greenish yellow. These are the the dark green, they are the older greenstone sequences, And the younger green, these corresponds to younger greenstone sequences. I'm just going to in the coming slides. I will explain the stratigraphic framework. This is the among the younger. This is the older, and this is the lower, and this is the upper. This is the Dharwar supergroup. Then this craton conventionally divided into two blocks earlier. This was 1976 when people started working. They based on the metamorphic grade and based on the abundance of the TTG greenstone association, they divided the whole craton into two blocks, the western block and the eastern block. So the dividing line is the mylonitic shear zone along this greenstone belt is on Chitradurga greenstone belt. Along the eastern boundary of the Chitradurga greenstone belt, there is a major shear zone. This boundary shear zone considered as the terrain boundary between the two distinct cratonic blocks. So, and more recently, last 10 years, lot of new structural fabrics mapping, geophysical profiles, then metamorphic records, then geochronology, UPB Zircon dating. All these together reveal several microblocks in the Dharwar craton. So, as you can see, the last 5-6 years, there is a lot of new work that indicates several microblocks. I will just show in the next, in the coming slides, what are these microblocks. And before that, I would like to make a small summary of the stratigraphic framework of the Dharwar craton. We have the TTG type peninsular gneisses. They have emplaced during 3600 to 3230 million years. The typical peninsular gneiss, the accretion stopped at 3230. These are the typical TTG suits. Then we have the greenstone sequences. In that, there are two distinct greenstone sequences. The older, stratigraphically, it is known as older Sargur group, and the younger Dharwar supergroup. And the older Sargur group, the volcanic rocks have been dated 3,400 to 3,200 million years, whereas interlayered sediments, the dated zircons from the interlayered sediments have been dated 3,600 to 3,230. This is the same range, and if you can see this range is more or less similar to the ranges of the ages of the TTGs. Then the younger Dharwar supergroup further subdivided into lower Babawudan group. I'm going to, in the course of this talk, I will just summarize these things.
Can you remind me which color was those?
In the map?
Yeah.
Okay, I'll just go back. Yes. See, these are the older greenstone sequences. They are confined mostly to the southern part, and this is known as the Sargur group. Okay, and the younger Dharwar supergroup. This is the lower Babawudan, the green color. This greenish yellow color. This is for the younger Chitradurga group. This is lower Babawudan group, younger Chitradurga group. Most of the stratigraphic framework only here, because we can see these are based on the unconformities between them.
Okay.
So the stratigraphic relationship between the gneisses and the older greenstone, it is impossible to establish because most of the contacts are tectonized. It is not possible to establish. It is only based on the ages we talk about their relationships. Okay. So, for example, here they are affected by the strong shear deformation. We have the greenstone belts. It is not possible, not at all possible to build the stratigraphic framework for stratigraphic record. So, all our discussions in my talk, the more importance, more details I am giving on the Western Dharwar, because here the relationships can be established, but here it is mostly dominated by the granites and the plutonic bodies, and the intervening greenstones are stretched, and all the contacts are tectonized. It's very difficult to see the contacts. Just I was mentioning that the younger Dharwar supergroup further subdivided lower Babawudan group and upper Chitradurga group. Then, in between these two cycles, this corresponds to one cycle of the craton building process. At the end, we have the metamorphism, emplacement of potassic granites, and the first stage cratonization close to 3 billion years. Then, on this cratonized basement, the younger sequences deposited. This Barbour group, we can see a clear angular unconformity at in the field. We can see the clear contact between the angular unconformity between the older sequences and the younger sequence. Then the younger sequence, the lower Barbour group dated 3000 to 2740, and the upper Chitradurga group dated 2740 to 2650 million years. So this is, we can in field we can see their contact, and that is also substantiated by UPB zircon data and also samarium, neodymium isochrons and the mafic to ultramafic rocks. This is about the western Dharwar. All the stratigraphy can be established. And the central and eastern Dharwar, in the eastern part, it is difficult to establish stratigraphy. Based on the ages, the events, we can build the events. Major outburst of juvenile transitional TTG and the greenstone volcanism 2700, 2600. Then the Sankeytide magmatism, crustal reworking, high temperature, low pressure metamorphism, and final cratonization during 2560 to 2500. And the final event, this is protozoic. These are the mafic dikes forms which are placed into the already cooled cratonized Archean crust. That is the last event. After that, this craton is nearly inert. No major tectonothermal event in the craton. Okay, now coming to the, I just mentioned that the more recent studies indicate several microblocks within the Dharwar craton. So based on the ages, geochronological data, isotopic data, and also the geophysical data, there are many profiles, geophysical seismic profiles across the craton has been initiated several years ago. So it indicates that the western block, this is the western block. The color I think you can easily make out. This is the western block, which is quite thick, 44 to 46 kilometers today, and it consists mostly the old crust and 3.6 to 2.7, and involved in two thermal events at one is 3.123, other one is 2.5. So this is the about the western block, and the central block. This is the central block from the east of Chitradurga boundary shear zone up to, this is the famous gold bearing Kolar greenstone belt, which continues further north as a Kadiri and further north up to here. So here the crust is relatively thin here, and mostly it is a mix of young and old crust. We have some large remnants of the old crust preserved on the eastern part of the western part of the central block. But the fundamental difference here is that it consists of large, several juvenile plutons, 2560 to 2500 million juvenile plutons, which are Sankeytide in affinity. They are totally absent here. So here we have the thermal event, high temperature thermal event 3240, 2620, 2500. This block affected by three thermal events. So this is the fundamental difference between them. We have no juvenile magmatism at the end of the Archean. This is the major part of the Archean, end Archean juvenile magmatism. Then the easternmost block, this is known as eastern block, which is also thin, even more thinner than this one. And here we do not have any remnants of old crust. This is only 2700 to 2500 million year old crust, and this is affected by only one thermal event at the end of the Archean. At the end of the Archean, all the three cratonic blocks, they are involved in one single thermal event at close to 2500 million years. So prior to that, this here two thermal events, here there is one thermal event. So based on these, three cratonic blocks have been identified. Then more recently, this is the cours block. So this has been identified as an independent a block, crustal block with independent history. because people argue that here there is no 2,500 million years thermal event. That means at 2,500 million years it was, they say this is an exotic block. So they say that during Mesoproterozoic this has been assembled with the Dharwar craton. Then some people argue that there is this is a Dharwar block. This is this is Goa. From here, this is the major shear zone. This is it's an independent cluster block, but this is not substantiated because the edges here and the edges here there is a transition. There is no real any break, no different thermal history, thermal accretionary. Everything is exactly the same. This is just a shear zone.
Can I ask some stupid question? So this crustal thickness you referred is today. Thickness of the today's.
Yes,
okay.
yes.
Not
Not Archean. People they speculate that in the Archean the crustal thickness is still more.
Okay.
This is what the people. This is today crustal thickness. Now this is we have drawn an interpretative cross section across the what I have shown across the three crustal blocks. So this is from west. This is almost close to the western coast, west coast. We have the greenstone belt, and we have the Baba Budan group, and then we have the further east we have the gneisses. This is the greenstones and the plutonic bodies, and we have the most of these major shear zones confined to the boundary between the gneisses and the greenstone belts. Probably they originated by the boundary forces because of the two contrasting materials with the different density. And this is the east-west, and from north-northwest to south-southeast, we have also drawn a cross-section. Baba Budan, this is the south in Haranashipur. This is where currently we are working. Very classical dome and basin patterns here. Then further south, from here when we go down, we are going to deeper and deeper into the lower crust, where we have the rocks of the lower crust with 10 to 11 kilobars. I mean, this is the minimum estimates. People put so many 15, 16 kilobars, but it is not realistic. What the realistic is 10 to 11 kilobars corresponding to the lower crustal depths is exposed. Now, I would like to summarize the history of the individual crustal block very briefly. The western block, I already mentioned the two types of the greenstone volcano-sedimentary greenstone sequences preserved here. The oldest TDs are preserved here. One of the most interesting aspects here is the very beautiful dome and basin patterns are preserved here. We can see on the satellite images the clear the domal structures. So this block formed, during the 3,600 to 2,700 million year history, but most of the crust formed during 3,600 to 3,230. So the younger crust is formed between 3,000 to 2,700. It is much, it's subordinate compared to the volume of the crust that produced during the 3,600 to 3,230 million years. As I already mentioned, this is affected by the two thermal event, one at 3.1 to 3, another one is at 2.5. Now, these are the lithologies of the older greenstone sequences. This is Servo, and we have, as you can see, these are the spinifex textured comatiites. They are very well preserved here. And we have also the 6M comatiites. These comatiites are they are characterized by very high MGO, 43 to 29 to 43% in general. Only few samples they show less than 29.8% of MGO. They are very rich in MGO. Some of them are 43%. And so we have the spinifex texture, and these are the pillows. They form philobrachia or flotabrachia. They are very well preserved here, and yes, again these are in the different greenstone belts. Mostly the philobrachias or flotabrachias. This is again spinifex. So the Western Dharwar it is a very fresh, very good comatites. You can see this is one of the outstanding features of the Western Dharwar. And we did some work with these comatites, and we found ages ranging from 3,380 to 3,200 million years. What we did is that we combined all these volcanics, and to define an isochron, we got reasonably good isochron, 3,300, combining all these samples from the different enrichment rates here, 3,352 million years. And these, they are characterized by high CaO by A2O3 ratios and low A2O3 by TaO2 ratios. And also they are characterized by a moderate to high GD/YYB ratios. All these characteristics indicate that they derive, the komatitic magmas derived from melting of different depths in the deep mantle, from 400 to maybe 250 kilometers depth. So these are the deep mantle derived ultra high temperature lava flows. So, and coming to their epsilon, we did some, they are characterized by very low ND content. It was very difficult to analyze them. In fact, when I started working on them, I did all these things in Japan, but I could not get, unfortunately, I could not get good data. Then I come back to France to Rennes. I did this, and I got this good data because they contain some of them are 0.2 to 0.3 ppm of ND. This was long ago. At that time, because today the sensitivity of machines and the analytical protocols, everything is advanced. At that time, we used to make a dissolution of 500 milligram of the sample. 500 milligram. Today, we don't do that. So this is the so that normally epsilon ND at time is 1 to 5, but there are some anomalous values in plus 7. That doesn't make any sense. Plus 7.4 we got. So I put only 1 to 5. So that indicates at 3.35 it's already highly depleted reservoirs. So this could be highly depleted, or this could be global differentiation as by what by it work, and this could be, I do not know. This is what we speculate because at that time, at this period of time, our data in the Dharwar indicate that the deep mantle reservoirs are highly depleted, and the upper mantle also highly depleted. That means probably there was an earlier crust building cycle before 3.2. During that time, they depleted. The depletion has occurred. Well, this is about the volcanics of the older Sargur group in the Western Dharwar. We have also some sedimentary sequences. These are the rocks from the only one greenstone bed. This is the bed we are working, Martin and me. So these are the sedimentary sequences where we have the conglomerates, very well preserved. Then we have the quartzite, and with the cross bedding. Then we have the ripple marks. I think you will be able to make out these ripple marks here, and we have the diagonal formations. I put a more on the closer view. Also, we have this one. These are the shallow water sediment sequences. They are very well preserved. These are the diagonal formations, and we have the penitic sediments also, but I did not include them. These are the photographs. And we did some work several years ago on the data zircon. So from the Varanasi-pur, this is this region, and this is from penitic sediment. We did some dating. This one from anywhere right from 3,350 to 3,500. One or two cranes, then a little bit older, 3,600 or even more. So that means this age corresponds to the minimum, the younger one corresponds to the age of the surrounding gneisses. That means they deposited at the time of the intrusion of the, or at the time when the TTCs are accreted. And this is further the east of the Varanasi-pur. Here slightly we have younger, some 3,250 to 3,400. One or two cranes, they are close to 3,000 460 or 70. Yes, in fact, they correlate with the surrounding the TTG basement. Yeah, these are the TTGs. This is one where we have the tonnarite, granodiorite, and injected by the trethamite along now it is in foliation. So these are the typical TTG gneiss what we can see in the western Dharwar craton. These are most of these are the TTGs are 3000. The oldest one is 3600, and the main event is 3400 to 3300. And transomites, they are injection. This is the terminal event of the TTG accretion. They injected, they are intruded into the TTG at 3230 million years. After that, there is no TTG accretion in the Dharwar, in the western block. Now, when we look into the timing and rates of the crust growth, this is the bar diagram that we prepare, and considering the granulation mechanism, TTG accretion, and also the tetrahedral zircons, they correspond to their provenance. The ages correspond to the accretion of their provenance. So right from 3000, a very small 3600 to 3400, but 3400 to up to the major 3000 close to 3100. Then there is another event 3000 to 2900. Then we have this small event, sporadic events here. So the major crustal growth here is around 3400 to 3200. This is the major episode of crustal growth in the western block. And in the 3400 million year old gneiss, we have the radiogenic lead in the feldspars separate, and that indicate an extended crust history up to 3800. And more recently, the tetrahedral zircons have been dated to 3.6, and also Martin has given a date of 3600 to even for one of the TTG samples. So that means we have the crust. In fact, we are looking for we have only few dates in the western block. We don't have many dates. I think more sampling, more careful sampling, more dating reveal maybe older crust. But I do not want to go into detail of this about in the TTG. The elemental data indicate that two types of TTG in the western Dharwar: high AL TTGs and low AL TTGs. High AL TTGs are characterized by low Mg, Fe, yttrium, but higher barium strontium coupled with high Sr by strontium by yttrium ratios, and with high total Re. So these characteristics we interpret in terms of the melting at the deeper part of the arc crust. I mean, this is our model. Or it could be alternatively, this could be also the lower part of the oceanic plateau crust. But we prefer the lower part of the arc crust to explain this because that indicates that the garnet remain in residue, these ratios. And plagioclase is only very little plagioclase left in residue. On the other hand, the low AL gneiss is characterized by the higher, is opposite higher Fe, Mg, yttrium, low barium, and low strontium, coupled with low strontium by yttrium ratios, and their Re content is also low without any significant HRE depletion. These characteristics we interpret in terms of their derivation by either by melting of arc crust in the shallow level, where garnet has not played an important role. Alternatively, this kind of gneisses can be also explained by the classical model by melting of subducting oceanic crust. But most people argue that subducting oceanic crust we cannot get TTGs. So still we prefer the shallow level melting of the arc crust to explain the low AL gneiss, because here the plagioclase play a significant role. It remains in residue within the stage. The melting occurred in the shallow level within the plagioclase stability field. Well, for the Archean crust that formed between 3600 to 3200 million years, this has been affected by a thermal event, and that led to the melting and generation of the potassic magmas, and all the heat producing elements have moved up, and that led to the first stabilization event, first cratonization of the western Dharwar craton. So this is the history of the oldest part of the western Dharwar. That is the oldest gneiss, and the associated older greenstone beds. Now coming to the younger greenstone sequences, I mentioned that the greenstone sequence, there are two greenstone sequences, older Sargur group and younger Dharwar supergroup. Younger Dharwar supergroup, the lower Baba-Budan group, this is the type area of the Baba-Budan group. This is the Baba-Budan cup-shaped Baba-Budan basin, and as you can see that this is a more rounded, and in the center there is a big depression, the flat area. This is the very dense jungle filled with all kind of life, mostly king cobras, pythons, and whatnot. You can see everything except lions, pythons. Yeah, we worked here with Dominique, and we encountered many times king cobras like that, and all kind of wildlife, including the many times leopards, just like that. So very dense. It's very difficult to enter here. So we did a strain fabrics mapping on the scale of the whole basin. We spent continuously 95 days in this basin to work. Okay, now look at this sequence here. So this is the basin. It starts with the conglomerate. Here we can see a paleosol on which the conglomerate is sitting, and then a clear angular unconformity is defined here. The basement shows stiff variation, and the cover sequence shows very shallow. We can see the bedding exactly like that. And these are the conglomerate. You can see the pebbles, which are very clean and quite big, so they involved in long transportation. After that, we have the thick, the basaltic flows. So probably they erupted on continental environment, where we have very beautiful amygdales and the vesicular vesicles. And this is when from the ground, when we see this is the kind of view we see from south. So all these are the very thick band formation. This is the Baba-Budan basin, and these are the conglomerates. They confined to the southern margin, and we have all these basaltic flows. And in between basaltic flows, we have the quartzites. Today they are quartzites. Probably they were deposited as a sandstone, or I don't know, maybe chert. And there are several interlayered. Each cycle we have the basaltic flow. Then on the top we have the quartzites. And then we have the basaltic flow, then we have the sediments, phyllites, then we have the tuffs, then we have the band iron formation on the summit. And yes, so these are the conglomerate. That shows variation in the pebble size, and this is the quartzite, which shows the cross bedding. Then we have from here, at that level, this is close to 2,000 meters from sea level. So from 1,000 meters, at least 800 meters, thick band iron formations are there. And this is one picture of the band iron formation. The whole region from this is band iron formation. Very, very thick band iron formations. Yeah. So we did some work on the band iron formations here in France only. Although I'm not a specialist of band iron formations, we did some work. So what we did is we took one core, then we cut, and individual layers we analyzed the elemental and isotopic compositions. And in some of the layers we have within this we have the alternately chert and iron oxide layers. So within the chert, in the where there is no recrystallization, we can see the nanometric particles. These are the iron oxides, where we analyzed, we find alumina, silica, phosphorus, sulfur, magnesium, calcium, manganese, carbon, and copper. And so this, we did some isotopic composition that gives some hint, not real convincing evidence for the biologic mediated reactions. It gives something -3, Fe56, we did also nitrogen isotopic composition that indicate either the N15, the heavier, it indicate probably some biologic mediated nitrate reduction reactions. We need to do more work on this. This is only one sample we did it on the Bababudal volcanics. Yeah, so these are these are the samples of the band error formation. They are similar to the other one, marble bar or fig tree from southern Africa. The one thing is that here they show positive European anomaly. This would be due, could be related to the input from the hydrothermal plumbing systems. And we do not have any significant cerium anomalies, and only very feeble cerium anomaly that would be related to the seawater, the conditions, redox conditions in the seawater. So, so these are some preliminary work we try to do on the band error formations from the Bababudal stone bed. You please remind me the time because I have to stick to the time.
It's quarter two, so still 10 minutes.
Okay, I try to summarize in at least in 10 to 12 minutes. Okay. So then that's about the lower stratigraphic group of the Dharwar supergroup, Bababudal group. The upper group, upper Chitradurga group. This is the Chitradurga basin, and actually the Chitradurga basin has two tectonic units. One is the proper Chitradurga, the eastern part. This is known as Java-Gandanalli Greenstone Belt. So they have a distinct characteristics. So this one, the large sediment component, no sediment component here, very less, and this is mostly the precipitate, and no detrital sediments here. So this we consider, we are working on this we consider two tectonic elements, and we can see that this is from the Chitradurga. So this is our interpretation is that this developed on the back arc setting within the continent, and this one is the continental margin setting. So there is less effect influence of, these are the volcanics, the basaltic volcanics, less influence of the older crust. So these are the phyllolavas, and these are the basaltic flows, and these are the phyllobrachias. And we did try to do some, this dating was did by the other groups, and we also did the Zircon areas of the felsic volcanics. They are mostly 2740 to 2670. This year there was no date, we did this dating, we obtained more or less the same age, 2740. But the isotopic compositions are different. From here there is more crustal contamination, here very less or no contamination. And rock types in the Chitradurga, we have the quartzites which are completely weathered, and we have the carbonates, stromatolitic, and then followed by we have the argillite, Grevac argillite sequences. These are the carbonaceous phyllites, and we have the banded hematite chert layers. This is this slightly higher level in specific regions where these hematite layers precipitate. Probably this is related to the redox conditions. This is stratigraphically this is considered as younger. This is yes. These are the volcanics that we have been we have dated 2677 to 2665. These are the volcanics in the higher stratigraphic level. These are the basalts in the lower stratigraphic level. Well, the error bar is still. I think there is some mistake here. This is not 15. This is 115 million years. The error bar is so high. And this this cycle from 3000 to 2700. This has terminated or culminated with another event of cratonization, the second stage cratonization. This is the final cratonization here, and this is evidenced by the intrusion of high potassic granites in the western Dharwar. So this is the 2006. That is the last major event in the western Dharwar. So coming to the the central block. The central block here, I just summarized this is the central block from eastern border of Chitradurga to the eastern boundary of the Kolar Greenstone belt here. So here, the most voluminous rock types are the granitites, and the greenstones are very thin, and only few thin greenstone belts. The more here the Ramagiri, Parakchala, this not Hatti, this is the Kustagi and the Hungun. These are the thin belts. Very minute chromatite, but the MgO content is much less compared to the it's only 18 to maximum 20%, and mostly basaltic volcanism here. And these greenstone belts are younger, 2700 to 2540. Mostly basic, the mafic volcanics erupted 2700, and all the felsic volcanics they erupted 2540 million years here. Well, the most abundant lithologies are the composite plutons containing the juvenile salicutites. So they are there are a large range of chemistry from 55 to 70% SiO2, and their epsilon values are most of the time either 0 or the positive, or some of them -1. They are come from heavy enriched source, and their elemental content much higher than the incompatible element components are much higher than the typical gneisses. And one interesting thing here is that the spectacular flat fabrics have been interpreted as the crustal flow during the accretion. A large amount of new juvenile crust has been accreted over a weak mantle, hot mantle. The crust could not accommodate thickening, and it started flowing laterally. At that time, this is the end of the Archean, at the time of amalgamation. At that time, this already cratonized cold lithosphere here, it cannot push this, so it started flowing longitudinally. Yeah, these are the rock types in the west, the central block. These are the older remnants. I mentioned that central block contains small older remnants and mostly the younger. These are the younger gneisses. These are the different phases of granitites. These are the salicutites, and these are the anatectic granites. They are intimate, they are interacting, and mingling features can be seen. These are the plutons in the central Dharwar. You can see the quite abundant. If you go to central Dharwar, if you make a traverse and you see everywhere this kind of plutons. Then we have the different kind of within the pluton. If you go to any exposure, we commonly see this different phases. The quartzbanjanite, monjogranite, and the granite, and we have the numerous synchrotonic fragmented dyes, and here also again these fragmented synchrotonic magnetic injections, and we have the very typical mafic magnetic enclaves where we can see the growth of the phenocrysts. This is a common feature. Coming to the timing of the crustal growth, as you can see here, the old crust from 3000, very few dates of older, more than 3,000 million years, 3000 to 3200 significant crust is there, but the main peak is between 2600 to 2500 million years. See, most of the plutons I showed, they intruded to embrace during this time. So the major, the greenstones are formed during 2700, 2540, but the gneisses are also in the same range. These are these gneisses are different from the West Dharwar gneisses because these are transitional TTGs. They show the characteristics of both TTGs and the salicutites. They are rich in both compatible and incompatible elements. So we classified them as their transitional TTGs. So major crustal growth 2.6 to 2.52, significant peaks at 2.7, 3.36 to 2.15 on 3 billion years. Thermal records 3.24. These are the texturally controlled in situ monazite dating 2.6 to 2.3 major events. Now the last one, the eastern block. This is the eastern block. Here there is only, as I already mentioned, that there is only young crust is preserved here. This is 2700 to 2500. We do not have, we try to date many samples, but all the samples which are giving dates either 2700 or younger, we could not get any older date. Even the other workers are also. People have dated also dated zircons. Lancaster has dated some dated zircon for one of these here. She got only the ages, yeah, 2560 to 2000. Those zircons come from the plutons. So here we have the mostly the nicest are transitional treatises, and we have the two greenstone show bimodal age distribution, 2700 to 2670. These are mostly the mafic rocks. 2580 to 2540. These are the felsic volcanics. These are contemporaneous with the transitional treatise. These are contemporaneous with the salicutite magmas. So there are two major events, and we have the salicutites, which are also quite abundant. Diatexites are anatectic granites here. But the last part is mostly made up of diatexites and anatectic granites here. This anatectic granite is formed by melting of very young crust, 2,700 million year old crust. They still preserve the isotopic composition of their similar to the gneisses. So these are the gneisses. This gneiss is 2,700 million year, and this is the monjodiorite. This is the salicutite, and here we can see in one exposure we have the this gneiss, mafic gneiss, 2,690. And we have a large budin of the porphyritic monjogranite, which 2,545, and this is a diatexite, 2,520 million years. In one exposure we find this, and here this is the magma chamber process where this anatectic granite injected by a large syn-plutonic mafic dike, where we can see the mixing and mingling process. Those two were my PhD students. Now they are working as assistant professors. The gneisses, again, these are the gneisses, mostly 2,700 to 2,600 million years, and most of the gneisses are between 2,600 to 2,700. These are the granites, and you can see the broken during the melting, during the shearing. The large mafic budins are broken, and they are along the major shear zones. They are being totally disrupted and moving. Well, coming to the timing of the crust accretion and the crustal growth, TTG 2,700 to 2,600 greenstone volcanism. Again, this corresponds to the same time. Granite 2,560 to 2,530. So this is the major event of the crustal growth. The high rates of crustal growth in both central and the eastern block during this period. This is the time of the intrusion of the juvenile granitites into the crust. On the scale of Dharwar, these are the major episodes of on the scale of the whole Dharwar. We have the major peaks, 3,400, 3,300, then 3,200 to 3,300 to 3,200, 2,900 to 3,000. 2,600 to 2,700, then finally 2,500. So on the scale of Dharwar craton, the available data, because here we don't have many dates, but here many people are interested to date the many granites. It's more simple to date granites. So we have the major peak at 2,500 to 600. So these are the different major periods of continental growth in the Dharwar craton. And now the question is, when these three, I say that these are the three microblocks with independent history, when they come into the cratonic framework. All the three cratonic blocks affected by one single thermal event at 2,500 million years. That means all of them were together at that time. And then now the question is when they have started moving. Our data, our fabric data, and also the ages indicate that they started moving, they started converging 2,560 million years as the hot orogenic crust started moving, and we have dated this, and then it lasted until 2510 because that time there was a apletic intrusion at the boundary between the two crustal blocks as being injected into the flat gneisses. So this one we interpret. So to this, the timing of amalgamation between 2560 to 2510, then the whole craton undergo the shear deformation, then it's finished. This is the last one. Okay, so I think I have only one slide. Okay, so this is the history of the timing of amalgamation of the three cratonic blocks into 3 microblocks into the cratonic framework, and then it completely, totally cratonized and cooled. And to this cooled Archean crust of the whole Dharwar, mafic dikes forms which run east-west, cutting across all the cratonic blocks. They have been dated 2,380 million years. So that means by that time the already crust has been cratonized and completely cooled, so into which the mafic dikes forms have been injected. So to summarize, the craton, 3 microblocks with distant thermal records and the accretion histories, which amalgamated into cratonic framework. One important aspect, I mean, this one I already mentioned that it is episodic crustal growth. Then these are the two important. I did not show many of these slides because there is a progressive change in the composition of the greenstone volcanics. There is a secular change in the composition. In the TTG, there is a secular change in the composition from the oldest to youngest. Classical TTGs to transitional TTGs to sonic-tides. This is a transition. And comatiites to comatiite basalts to basalt to boninites. This is it in the greenstones. So this clearly indicate that this could be linked to the evolving geodynamic processes. We interpret, or I would say we speculate that this could be related to the plume-dominated tectonics in the early 3600 to 3300, then arc-dominated processes progressively more and more dominate to the end of the Archean. So thank you very much for your attention.
Thank you. Are you any questions?
So what are the arguments, basis of the arguments for the hydrous melting? You, at some part in your talk, you mentioned that some of those properties of the gneiss are hydrous, derivative of hydrous melt.
Yes,
so what are
the argument is that when you have built the arc crust is already contained the hydrous metals. When you subducted the oceanic slab, when you produce the melts, those melts, when they move up and crystallize the arcs and those arc crust, it's already contains some hydrous minerals.
So it's the presence of the reconstruction basically argues for the presence of the
yes,
okay.
You have already this one.
Okay.
Just a question. Your thermal event at 2.5, is it directly linked with your accretion of your different blocks?
This is yes, this related to the last terminal event of the amalgamation is linked to the mantle upwelling and the huge amount of the outburst of the magmatism. So this during that time the hot organic crust started moving and amalgamated. This is the argument to what we put. So that means this time because all this amalgamation through the convergence. So at the end, what we interpret is that, at least we speculate that downgoing oceanic the slabs they cut off, and that lead to the when they go down the mantle upwelling. That caused the it is not really the plume, because normally plume it associates with some automatic magnetism, but we don't have at this time no automatic magnetism. This is a mantle upwelling that caused the enormous outburst of the crust between 2560 to 2520. So this is the interpretation. This is the heat source for the metamorphism, crustal reworking, and all the terminal Archean development of the extensive flow of fabrics, lateral flow of the hot crust. So this is the interpretation.
No, it's not minimal age. It's you interpret as the age of. It's not give you a minimum.
No, not minimum. Because we have clearly that I just mentioned that 2,500. This is the youngest one at 10 million years. That occurs at the boundary of the two blocks.
Okay.
The boundary between the western and central, and the central and eastern, we have the younger granites which are more apletic. So this kind of granites, apletic, small plutonic bodies, probably they are the result of the amalgamation of the crustal block through convergence.
So you said that the western block is quite thick,
Yeah.
and you also show that from 3.4 to 3.2, the TTGs that are generated at greater and greater depth. So I was wondering if...
No, I did not say greater and greater depth, at different depths. This is my interpretation, that there are, you can choose. I say that they are produced, the TTG melts produced between 3,400, even 3,400. We do not know. Many people argue that at that time there are no plate tectonics. This is the plume or something. But what we put that it is very difficult to differentiate between the mechanism of melting, whether it is the different depths in the arc crust or at the different depths in the oceanic plateau crust. So we say that this is our interpretation that the arc crust, thickened arc crust, and at depth, greater depth, we produce the melts where the plagioclase is not anymore in residue. Only very small plagioclase remain in residue. Large part enter into the melt. That accounts the high alumina, high strontium, high barium in the gneisses, and also at depth the residual mineralogy mostly consists of garnet. So that deplete the HRE and Y. So this is based on the elemental composition of these gneisses, high AL gneisses. We argue in this way. The other one we interpret in the shallow depth because they are low in strontium, low in barium, high in yttrium, because garnet is no more stable at that shallow depth, and plagioclase is in residue. That is the reason. This is just an argument. It could be the oceanic arc crust. This is our preferred model, but it could be also the thickened oceanic plateau crust. Or more recently, you are also one of the authors in this paper. The convergence of the oceanic plateau crust can also produce TTGs. So it could be this kind of scenarios.
So at all different ages, you have both the low and high aluminum group? I thought that the low aluminum group was always the oldest gore gneisses in the high aluminum.
This is a good question, but this is mostly this one is mostly for specifically to 3,350 to 3,230 million. Only this time range we have made this argument. Maybe we have older than we do not have many ages. This is just what the data that is available we interpret. Maybe if we can have more sampling and more ages, maybe we may get more new database where we can more precisely we can argue about these aspects.
So there's no relationship whatsoever between depth of melting and age of these TTGs?
That we did not address because we have only we have two generations. One is the TTG between 3,300 and 40. That what I put in my paper in Tricam Research 2015, and this is 3,340 to 3,301 and 3,230 diaperic transamite. So we combine this. So diaperic transamites, most of them are IAL. They are generated at great depth. And only the TTGs, typical tonalite and granodiorite, we have the high AL, low AL.
Okay, so we can maybe carry on the discussion after I let people go. Thank you again for coming. Thank you for
Thank you very much.
And our visitor is still here for a week. Yeah. So if you have any questions, you can go and see him. When is this happening? Exactly. Because what's your sampling is?